And there will be several assignments and a quiz as well. And there will be a quiz on Friday regarding the algorithm I'm going to cover today for that structure. Successive approximation register, ADC, analog to digital converter, okay, or SAR ADC. So first you need a sample and hold circuit, the samples and hold the values at that moment. So analog input comes in, you do a sample and hold. So for example, it's holding this value here. Just at the analog input at the moment will be held and becomes a DC voltage. So we'll look into the sample and hold circuit details later. It's a lot of things to be covered. But now let's just assume that there's a certain sort of capacitor is able to hold it at a certain level. So the input will be captured and be held. And then you'll have the opportunity to do the ADC conversion because the DC voltage is held over there, right? It's for a certain period of time. It's a DC voltage is not changing. So we are assuming that this input is not changing, but actually it's changing, right? So if you zoom in at this point, the sine wave looks like this, okay? Like this, for example. But the thing is, it's being sampled, okay? Sampled, and it's being held for a certain period of time. Because you can do this sampling really quickly, so you're actually tossing the information over here. So in that case, for a certain or finite number of bits for the ADC, you are getting definitely not 100% all of the data being converted into your digital signal. Okay, so that's why there are errors. There are errors eventually. So the higher resolution will give you less errors and more accurate of the ADC output, the digital output. Okay, so first you have to use a sample and hold circuit, and then the next stage is the comparator. We'll look into the comparator's behavior really quick, plus minus, and the output goes to a structure called SAR register. That's a digital logic. It consists of a bunch of registers. It's a sequencer and the code register, so two structures. We'll learn the circuits in detail today. And so after that SAR structure, for example, we are doing an 8-bit conversion, 8-bit. So there will be an 8-bit digital output. So we need a DAC. DAC. It could be a R2R string. Okay, we learned at the very beginning of the semester, R2R DAC. Because the DAC receives digital inputs and output analog signal. So eventually, analog signal will be used as the input to the inverting term of the comparator. So I had a old structure of the comparator that was used for the course project in the previous years, but I didn't like it. So probably this year, so this year we'll change it to a newer version. I'm sorry for the. We'll see how it works today. Okay. So this one, the DAC's output is being fed back to the DAC for the comparator, and the thing is, these values keeps changing. So we expect a certain output over here. So where is the output? That's the converted results. It's being fed into the DAC and being fed back to the inverting term of the comparator. So these are actually outputs. These are outputs. So we just need to connect them to a 8-bit bus over here. So the problem is always changing. You are getting some intermediate values, which are not the final results. It takes a certain number of cycles to finish the conversion, and you only need the very last one. So in that case, you need a digital control logic here. It's just eight D flip-flops in parallel. I just call it, it's a door latch or door D flip-flop, doesn't matter. I just call it door latch. It's very simple structure, just 8 D flip-flops. So you have to program a certain timing circuit, to wait until the 9th clock cycles to kick them out. So these are the final results. The A bit is going to be D7 to D0. So input, output, analog input, digital output. Okay, that's what the ADC does. All right. So how this works? The key component here is the SAR register. We have to implement that ADC conversion algorithm over here, and this comparator is really simple. So let's start with the simple one first. And this one, we assume that we can capture an analog input and hold it over here. Okay, so this is relatively simple. And this one is really fundamental. So let's start with this one. So the comparator circuit is basically an op-amp, operational amplifier. All right, this is VP, VM, plus minus, VP input, VM, and this is V out. So V out equals what? Some circuit 1 basics. V out equals what? So what is in your mind right now? Are these all these closed loop gains or something else? So what's the difference? Could you tell me what the difference is? It's a super simple question. Could be in the interview. This closes the open loop, right? So if it's a closed loop, what is this called?
Inverting or something?
Yeah, so this is closed loop. It's called inverting amplifier, right? Inverting configuration. So it's an inverting configuration. And what's the voltage gain here? VL equals what? Minus RF over R1 times V in. What is this called? Because input goes to the non-inverting terminal, so it's a non-inverting configuration. So you can tell the gain for this one is VL equals 1 plus RF over R1 times V. So it's not getting inverted. It's not getting inverted, so the input and output are in phase, right? But this one's getting inverted, so the input and output are how much? 180 degrees shifted. Okay? Some fundamentals of the closed loop op-amps. But this one doesn't have a closed loop. Doesn't have a feedback. Okay, so what's going to happen here? So VL equals what? VP minus VM times AOL. So AOL is called open loop gain. Open loop gain. And this one is usually huge. For example, 1 milli. Okay, 1 milli. So that means a little change between, so if they are not equal, a little difference between BP and VM, it's going to cause a huge VL. But the problem is you have the real to real, right? It's usually, let's say 5 volts to 0 volts. And your power supply cannot support that huge difference. So what's going to happen eventually is it's going to saturate at the rails. Saturate the rails. Okay, so eventually, if I have, for example, VM at 2.5 volts as a reference voltage, it's VM, and VP, I put an analog input into it, doing this. This is VP. So output looks like what? So what the output would be?
It would get clamped.
Get clamped?
Just, it would stop at the threshold.
Mm-hmm. Yeah, so let's say for this period, what's gonna happen for this period? Who is larger? Which one's larger? For this period, which one's larger? This period, which one's larger? VP or VM? VM is larger, okay? VM is larger. If you plug it into this equation, what's gonna happen? So this will be a negative number, right? So negative number times this huge gain, you're getting like a negative 1 million. Is that possible? No. So what's the lowest potential in the circuit? 0. So it's gonna saturate 0 for this period. So that's the output, that's VL, okay? Puzzled, right? Yeah, since we didn't have a lot of op-amp experiments in the past, I believe. So whenever VP, at the moment VP becomes larger than VM, so as soon as VP becomes larger than VM, this becomes positive. It could be like 0.001 millivolts, whatever, okay? It's just a little bit larger than it, and this becomes positive. And this little positive number times the huge open loop gain, and it's still a huge voltage. For example, 1 million times 0.001 millivolts. It is still giving you, no, it's not a good example, like 0.1 millivolts, for example, right? So it's going to give you like 10 volts. But do you have 10 volts to supply from the supply? No, the supply can only give you 5 volts. Can only give you 5 volts. So eventually, it's going to saturate at 5 volts. So whenever VP is larger than VM, it's giving you 5 volts. And whenever VP is smaller than VM, it's giving you 0 volts. So that would be the comparator's output. Comparator's output. Okay, so if there's no closed loop or feedback resistors, and this op-amp is being operated under the comparator mode, but these are different. Keep in mind, these are different. Okay, another quick quiz question: do you usually use large gains for one stage when you are trying to amplify an analog signal or no? Are comfortable with amplifying the signal for like 100 times usually? Yeah, it's usually not the case. Okay, usually don't make the gain here larger than like 20. It's introducing a lot of so there's a mismatch over here, so it's amplifying or DC mismatch a lot. So eventually it's going to saturate. So usually if you need to amplify for 100, for example 100 times, you add multiple stages like 10, 10. So 10 times 10 becomes 100, and you add filters in the middle. Okay, this is really important stuff to learn about. This one is different. So this is not being used. It's not being used to amplify a small analog signal from the sensors, but instead it's used as a comparator, comparing the two inputs and giving a digital output. So if I draw a comparator like this in the future, in the quiz, are able to draw the output like this. I may swap the two terminals. For example, I give a 2.5 volts. It could be like 1.5 volts, doesn't matter. Try it. Here's 5. For VP. So VM. So how would you draw V out? V out. Looking at this period, what's happening? VM is larger than VP. No, VP is larger than VM, right? So for this period, you are expecting a 1. And for here, expecting a 0, right? Any questions on this? VP larger than VM, so you are getting a 1 because it's a VP. Output equals VP minus VM times gain. All right. So now let's look at the SAR block. SAR block. It follows an algorithm. It looks like this. In case we have a 10 volts VREF equals 10 volts, for example. And so it starts with 1000 for the conversion, and if I'm trying to, for example, V in analog, like this, V in, right? So at this moment, this V in equals 5.2 volts, 5.2 volts. So now the SAR ADC is going to start working really hard to convert that 5.2 volts into a 4-bit digital number. And the SAR block is going to do this. Before we think about the structures, let's just think about what we need from the SAR, okay? Then we design the circuit. So this is what we need, okay? So it set the output to 50% of the full range first. You can see this 10 volts, and this is 5 volts. This is 5 volts. Why? 10 volts divided by what? 2 to the 4th as a whole range, and times this number here, which is 8. You are thinking about 2's complement? No, it's negative 8. Is this 8? Is this 5 volts? Is this 5 volts? If the full range is 10 volts. 10 volts divided by, it's a 4-bit, right? So you have totally 16 stairs, or 16 different levels. So 10 divided by 16 times 8. because this number is 8. So it's 10 over 16 times A, which is 10 over 2, right? Which is 5 volts. This is 5 volts. Start with 5 volts first. So the circuit has to be able to reset some sort of D flip-flops and give you this output at the very beginning to start with. That's the first value you have. And then this one goes through the DAC, Oh, this is 8-bit, but just imagine it's 4 bits, right? So you are starting with 1, 0, 0, 0. And this one goes through the DAC, giving you 5 volts. 5 volts. We call this VDAC, 5 volts. And is this value changing? Is value changing or no? Is value changing or no? No, it's the input, right? Sample hold, it's holding that 5.2 volts over here. It's waiting for the conversion to be done. So the first time I'm giving it's like it's trying to guess what the number is and compare, right? So it's giving a 50% of the value of the full range first, and then compare with the input. So if Vin is apparently Vin is smaller or larger than 5. Definitely it's larger than 5, right? So what you want to do is plug 1 at the front and shift all the bits to the right by 1 bit, by 1 digit. So that's the SAR's output for the second time. This is the number you plugged in, and these are the original numbers over here being shifted to the right by 1 digit. So plugging a 1 here, plugging a 1 here. And so what is this number now? Times what? 12. What is it? Let's calculate it. It's 10 divided by 16 times 12. 7.5. Right, 7.5. So where is 7.5 over here? Where is 7.5? Here, right? If I compare, what's the output over here? What is the output? BPVM. What is the output of the comparator? You don't have negative. So the lowest potential is 0 volts. 0, right? VM is larger than VP, so you're getting a 0 at the output of the comparator. So it becomes 0 because VN is smaller than VDAC. So next state becomes 1, 0, 1, 0. Why? Because this part, original part, is being shifted to the right, and you are plugging a 0 here. So what is this number? 10 volts divided by 2 to the 4th times 10, right? What is it? Divided by 16 times 10. 6.25. So 6.25 will appear here, here. What is the output of the comparator? 0. Because VP is larger than VM. smaller than VM, so you are getting a 0 again, right? So the value here becomes what? 1001. So this is the one keeps being shifted. It's being shifted. This is the original one here. That's a newly plugged 0. Okay, that's the one you plugged in there. This is the one you plugged in there. So what is this value? 10 volts divided by 2 to the 4th times what? 9, right? And this is 0.625 times 9. This is 5.625 volts. Okay. Let me know what the digital value, digital number is. So V in smaller than VDAC again. So what's the code output from the SAR? One zero zero zero. Why? Because the 1 is being shifted out. You only have 4 bits holding the values. So the original 1 here has been shifted out and only leave 1000 here. And that's a newly plugged 0 from this comparison. So count how many cycles do you need? 5. So you need an n plus cycles. So n is a resolution of the ADC. What's the resolution of this ADC? 4-bit. Okay, so 4-bit ADC. That's the resolution of the ADC. So 4 bits. And eventually, the ADC's output becomes 1000. And you can see originally we already set of 10000. Okay, eventually it's still the same value. It's not changing. It's just because 5.2 volts is not very different from 5 volts, and the resolution of the ADC is so low, it's not able to resolve it. You want to try a different number here? Let's try a different number, okay? So this time I'm going to let you guys tell me the comparison results in SAR code after each step. So analog input, okay? So for example, it captures this point, which is like 6, let's just say 6 volts. 6 volts. Right? Keep in mind, this will be on the quiz on Friday. So 6 volts. What is the first SAR output? It's whenever everything's getting ready, it's just reset. Everything has to be reset. Set everything has to be set, and get everything ready, right? So there will be an initial output from the SAR. Initial output from the SAR, and that is what? Yeah, just 100s, right? Always 50% of the range. So you're just throwing that 50% of the full range into the system and to start with. So you can compare with the analog input. Doesn't matter which is larger or smaller. Doesn't matter. The SAR logic is going to handle that. But you just need to have a number to start with, okay? And that's going to be this. We know this is 5 volts, okay? We know this is 5 volts. So V in is what? Smaller than VDAC because this is 6 volts. No, sorry. V in is larger than VDAC because VDAC is 5 volts and V in is 6 volts. Keep in mind, V is the analog input. Analog input. And that's V in. So what's next digital code over here? Keep in mind, we're shifting the whole thing, the initial number here to the right by 1 digit. We plug in the comparator's output.
0, 1, 0, 0.
The comparator's output, so which is V in? This is V in, right? This is analog input. So analog input is being connected to where? Non-inverting or inverting terminal. VP or VM? VP or VM? VP, okay? So VP is larger than VM right now. So the output is what? 1 or 0? 1, right? 6 volts, 5 volts, which is larger? This is larger, right? So in that case, comparator's output is 1. Because the gain is VP minus VM times the open loop gain, right? So VP is larger, you're getting a positive number times a huge gain is getting to the top rail, which is 1, right? It's getting 1. So what's the next digital code over here? What's the next digital code?
1, 1, 0, 0.
Yep. These are the original code being shifted, and this is the new number here, new comparator's output. Yeah, since we know this number from the last example, so what is that number? 7.5 volts, right? So 7.5 volts comes down from the SAR and goes through the DAC, becomes the next VDAC. Becomes the next VDAC. So now V in is smaller than VDAC. What's the next digit? What's the next code? Keep in mind, you shift this one more time, you're plugging the new number in here. You're plugging the new number after the last one. You're plugging the new number after it, but you are shifting the original code to the right. So what's the next one? What's the next one? 1010, because this is the old code and this is the new number, comparator's output, and we know this number is what? This number is 6.25 volts. So this is what? VDAC, right? So what's next? All right. What's next? So V in what? VDAC. Bigger. Yeah. So what you want to plug in here? 1. No difference. 5.625. So if you got a 6 volts input, you are getting a 5.625 output from the DAC or from the ADC, or 1001 from the ADC, but eventually you need a DAC. Wait, no, sorry. So the ADC is going to output 100 makes the digital output, right? But in theory, this is like 5.625. Okay, so it's not really accurate. It's only 4 bits over here. Any questions on this? Any questions on this? No? Now let's see how to implement this algorithm in circuit, in hardware. It seems that we have to create this first. So we need 5 D flip-flops. 5 D flip-flops. In case that something on the top, we don't know the structure yet, but assuming that something on the top can give us a 1 0 0 0 0 at the very beginning, and these D flip-flops are active high, so they're active high D flip-flops, which means if you give a 1 to the set pin, it's going to set the output to 1. Okay. Well, these are the outputs, the Qs. If you give a 1 here, it's going to set it. So it's not going to take the input or the data from the D anymore. So Q will be set. So it seems like this is fine as a first cycle at the very beginning. And we are assuming that the shift register or the sequencer is able to shift this one to the right and leave a 0 in front of it. It's assuming it's going to work, okay? Then if this 1 becomes here at the very beginning, we're getting a 1 zeros, right? Only taking these outputs as a SAR's output. So these are that's the number in that little circle here for each state, each one. So this is at the very beginning. And then we use the output from the next stage as a clock input to the first stage, and just keep doing that for the following stages as well. Okay, and then we connect the comparator's output. That's the output from the op-amp, okay, from the comparator, to here, 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 here. We don't need this one. This one's just providing a clock for the previous stage. So if we connect a circuit like this, let's see if that works. Okay, see if that works. So whenever this is being set, you are getting a 1 for the Q of this stage, right? You are getting a 1 zeros, no problem. And next time you are getting a 0 1 0 0 0 from the sequencer, assuming the sequencer works, and you're getting a 1 here. So what's going to happen? What's going to happen for the next? Take a look at it. So keep in mind for the D flip-flop, if you set it, it's not functioning properly. So if you set it, you're definitely getting a 1 at Q, right? If you don't set it, which means if you give a 0, because these D flip-flops are active high D flip-flops, which means 1 will set it, but 0 is not doing anything. So if you give a 0 to set, it's operating as a D flip-flop. It's taking D into Q at every clock cycle. And we assume it's a rising edge triggered. So what's happening here? If this 1 shifted to here, and this will be set, and this will not. Okay? This will not. If this is being set, Q is what? Q becomes what? 1. It was 0 and now it's 1. So you can see there's a rising edge. And that 1 is shorted to the clock of the previous stage. So the rising edge is actually given to the clock pin of the previous stage. So you are seeing a rising edge over here. And that rising edge is going to do what? It's a rising edge triggered. And now it's 0 at the set pin. So the D flip-flop is not being set. So it's operating as a D flip-flop. So the rising edge is going to do what? It's going to take D to Q. It's a data flip-flop. It's going to pass D to Q. So what is this one? Let's call it A3. That's the first comparator's output. Okay, so this number will be replaced by the comparator's output. Is that what we expected? Look at this one. We do want to plug that comparator's output into the MSB spot. It works. And that original one is getting shifted. And the original one is getting shifted. It's gonna work. Okay? Now let's see the next stage. So these are not changing. Why is it not changing? Why is there still zeros? They are saying, hey, comparator is also being fed into the D's of the following stages. Why the comparator's output is only being passed to the Q of the first stage, but not the following ones? Why?
Because it's being shifted over, so it's not needed.
No, it's shorted. It's physically shorted. See, comparators, it's a wire, same wire shorted to all the D's. But only the first one is getting A3, getting the updated output, but not the rest. And the rest keeps the same, remain the same. It's not changing. Why?
It was already set.
It's not being set. Zero is not being set. One is set. It doesn't have the edge. Is there a rising edge for this guy? Is there a rising edge for this guy's clock? No, it's a zero. Okay? But doesn't matter because this one is being what? It's being set. Because the one is getting shifted to this stage. So this guy is being set. So you do expect a 1 here. Okay? But for the following stages, they don't have a 1, it's not being set, and they don't have a rising edge of the clock. So it's not doing anything, it's remain the same. It's not changing. Make sense? Okay. What about next? 0, 0, 1, 0, 0. So magically the sequencer is able to do this job. Look at the sequencer later. Okay, but now we assume that sequencer is able to shift this one and plug zeros in front of it. Okay, so 1 now shifted to here. What's going to happen? You see, this guy will be, so 1 moves to this set pin. What's going to happen to this one here? What's going to happen to this one here? To this Q here? Being set. Because 1 is arriving, so Q will be set. Okay, if this is being set, what's going to happen? There will be a rising edge for this guy. Okay? If there's a rising edge for this guy, what's going to happen? So the new comparator output will be placed at this Q. Let's call it A2. What about this one? What about this one? It won't happen at the same time, so still keeps the previous value, which is A3. And all the following ones are not changing. So just keep doing this for a few cycles. Eventually you are getting A3, A2, A1, A0 for the output. If you draw a table here for all the results, D3, that's outputs, okay? D3, D2, D1, D0, and here's a comparator's output. So D0, cycle 0, let's assume there's nothing in there and no compare output before we start anything. For cycle 1, for the first cycle, we reset everything. And then we got an A3 as a comparator's output. And for cycle 2, we plug that in here as MSB and shift everything to the right. And this number, this value is giving us A2 for the comparator. And that A2 is being plugged in here. And this result is giving us A1. And A1 is being plugged in here. And this compared to the comparator's non-inverting terminal is giving us A0. And eventually, you are getting this. So 4-bit ADC and you need 5 cycles, is n plus 1 cycles for the 4-bit ADC. And now the question here is, why is the comparator's output is directly serving as a bit, the digit over here as an output? Why is that? Because the circuit connection, right? Because the circuit connection. Because whenever, so whatever the comparator output is, if it's a 1, you are putting a 1 in here. If it's a 0, you are putting a 0 in here. That's why these are aligned. Okay, A3 is A3, A2 is A2, A1 is A1, A0 is A0. So now let's look at the sequencer circuit. Sequencer. So we need something that is able to do this job, right? Create this one first and then keep shifting it to the right and plugging zeros in front of it. What can we do? So these are the inputs from the sequencer. So for the sequencer circuit, 1, 2, 3, 4, 5. It's a set, it's a reset, 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 reset. Okay, Q, D, Q, D, Q, D, Q, D, Q, Q to D, D to Q. And there should be input, and the clock is synchronized. Clock synchronized. Now we're getting output from here to connect to your code register at the bottom, like this. So you connect your set or reset signal to the set for the first one, even though we call it reset. This is resetting the ADC, but the thing is we connect the reset to the set of the first one. However, connect the reset to the reset of the following ones. So whenever, assuming this is active high, whenever we give a 1, what's going to happen? Give a 1, what's going to happen? The first one is being set, but the following ones are getting reset, right? So we are getting 1, 0, 0, 0, 0. Okay? Because this line is being shorted to the set for the first one, the reset for the following ones. That's why when you give a 1, trying to reset it, this is getting reset. This is getting set, but all the following ones are getting reset. It's giving a 0. So it's not operating as a DP flop, but it's being set and all the rest are being reset. Okay? and then you change this one to 0 immediately after the next clock cycle. If this one becomes 0, what's going to happen? This becomes 0, so this is not being set, and all the rest are not being reset as well. Okay, and for people who are in embedded, you probably just did a serial in parallel out. So this is exactly a serial in parallel out shift register, because this is the input for the first one, and it's being shifted to the right, and you are having a parallel out over here. So the next clock cycle, you are giving a 0 to these set and reset pins, and all these become a normal D flip-flops. So it's going to do the D flip-flop job, okay? And then every clock cycle is going to shift this one to the right by 1 bit, okay? And all the previous ones are taking the Q, the D's are taking the Q from the previous stage. But however, we hope this one can get new zeros being shifted to the right instead of something else. So what should we do for here? Think about it. I'll give you the answer on Friday. Okay. So the question is, how do we deal with this pin? Review that SAR logic, SAR algorithm. So all the state diagrams like this, and we'll have a quiz on Friday. I'm gonna directly give you a random analog input and let you draw all the state diagrams. Okay, it's gonna be 4-bit ADC.